next speaker, Durán. We're moving from mathematical physics to a more orthogonal polynomial theory, and we're going to talk about invariant properties of Wronskian type determinants, classical and classical discrete orthogonal polynomials.
Thank you, Manuel. Well, first of all, I would like to thank the organizer for inviting me to this meeting, and congratulations to Natig for this nice meeting. So I'm going to talk about determinants whose entries are classical or classical discrete orthogonal polynomials. This is a long study subject. Maybe the first result is the Durán inequality, which establishes that if you consider these 2 by 2 determinants whose entries are consecutive Legendre polynomials, then the sign of the determinant is constant in minus 1, 1. 13 years ago, later, Carlin and Sego generalized Durán inequality for Hankel determinants of arbitrary size k, even arbitrary size. Hankel determinant of this form, you consider here k consecutive polynomials, and then the sign of this determinant is again constant when the polynomials are Gegenbauer, Laguerre, or Hermite polynomials. Carlin and Sego also consider this Casoratian determinant of n consecutive polynomials. They study the sign of this determinant for when the polynomial Pn are some families of classical discrete orthogonal polynomials. However, they were interested in the sign of the determinant, and they did not notice certain very surprising symmetries and invariant properties that this determinant enjoy. This is I'm going to show now one of these symmetries. I'm going to consider Charlier polynomials, which I'm going to denote C and A. A is the parameter of the family. I am going to normalize the Charlier polynomial so that the leading coefficient is 1 over n factorial. And I'm also going to consider a finite set of positive integers. And I'm going to define this Casoratian determinant, where in the rows the index of the Charlier polynomial run in this finite set of positive integers. I have also to introduce an involution in the set formed by all finite set of positive integer. This involution is defined in this way. If you consider the finite set F, the involuted set I of F is defined in this way. You consider the consecutive integer from 1 to the maximum element of F, and then subtract this stuff here, this number here. Roughly speaking, the bigger the holes of the set F with respect to this set, the bigger the involuted set. For instance, if the set F has no holes, then the involuted set is just a singleton. And if there is a big hole here, then the involuted set is very big. So the set F and the involuted set can be very different. And so the number of elements of F and the involuted set. It is easy to see that if the set F has k elements, then the number of elements of the involuted set is just the maximum element of F minus k plus 1. Okay, so I'm going to take this Casoratian determinant, and I'm going to change the set f to the involuted set I of f, x to minus x, and a to minus a. So in principle, these determinants are very different. For instance, this has size k, and this because the number of elements of f, and this has size m, the number of elements of I of f, and this size can be very different. So it's quite surprising that these two determinants are actually the same, except for a sign. Okay? So this determinant is equal to this determinant, except for this sign, minus 1 over this number, which depend only on the finite set f, and is defined in this way. By taking limits here, when the parameter a goes to infinite, this symmetry produces a symmetry for Wronskian determinant whose entries are Hermite polynomials. Okay, I'm going to write h of f for the Hermite polynomial of degree f. So this is just the Wronskian of Hermite polynomial when the index rank in the set f. I normalize like this. And then there is this symmetry. If you change the set f to the involuted set I of f and x to minus I x, then these two determinants are equal except for a power of I. Okay, so in this talk I'm going to show an approach to this, a way to prove this or to find this kind of symmetries. There are similar symmetries also for Meissner and Hahn and Laguerre and Jacobi polynomials. And the purpose of this talk is to show how to get these symmetries using Kral discrete orthogonal polynomials. And in the second part of my talk, I'm going to show that these symmetries, there is some deep connection of these symmetries with many other physical and combinatorial problems. I'm going to show that these symmetries are related to the equivalent between eigenstate adding and deleting Darboux transformation for certain solvable quantum mechanical system. And if I have time, I will also show that there is a connection with the Selbert type integrals and constant term identities of certain multivariate Lorentz expansions. Okay, so I'm going to, first of all, I'm going to show how to get these symmetries. So I have to introduce these Kral orthogonal polynomials. They are a generalization of the classical and classical discrete orthogonal polynomials, and they are defined as follows. Kral polynomials are orthogonal polynomials that, in addition, are also eigenfunction of a differential or different operator of order k greater than 2. Okay? The case k equal to 2 gives the classical and classical discrete orthogonal polynomial. Well, the first sample were introduced by Harry Kral in 1940, and this is because they are called Kral polynomials. Harry Kral classified all families of orthogonal polynomials which are common eigenfunction of fourth order differential operator. For differential operator, the recipe for constructing Kral polynomial is very simple. You have to take the Laguerre polynomial or the Laguerre or the Jacobi weights, and then assume that one or two of the parameters, alpha and or beta, you have to assume that these parameters are non-negative integers, and then you have to add a Dirac delta at one or two of the endpoints of the interval of orthogonality. You have to add, in the case of the Laguerre polynomial, you have to add a Dirac delta at 0, and for Jacobi polynomial, you have to add a Dirac delta at 1 or at minus 1 or at both. We do not know any sample of Kral polynomial associated to Hermite polynomials. After the 80s of the last century, a lot of effort has been devoted to this issue of Kral polynomial associated to differential operator with work by many colleagues and friends. The situation for discrete, when you consider a different operator, is rather different, because the problem of finding Kral discrete polynomial was open during many decades. In fact, and the reason probably was that what we know for differential operator has seemed to be of little help, because when you add a Dirac delta to the classical discrete measure, that seems not to work. In fact, Digaski in 1991 explicitly posed the problem of finding these Kral discrete polynomials, and he suggested to add a Dirac delta to the classical discrete weight and see what happens. But 3 years later, Babin, Van Heringen, and Kukuk gave a negative answer to the ASCII suggestion, because they added a Dirac delta at 0 to the Charlier and Meissner weights, and in fact they constructed different operators with respect to which the corresponding orthogonal polynomial are eigenfunction, but unfortunately these different operators have always infinite order, and this is not very exciting because this always happens. Okay. Yes, 4 years later, I found the first example of these Kral discrete polynomials, and the recipe I used to find this Kral discrete polynomial was very simple, but very different to what happened in the for differential operator. The recipe is just instead of adding Dirac deltas, you have to apply a suitable Christoffel transform to the classical discrete measure. In other words, you have to multiply the classical discrete measure by a suitable polynomials. Depending on the classical discrete measure, you have more or less possibilities. So this is what happened, for instance, for the simplest case, that is the Charlier weight. Okay, so consider this is the Charlier weight, and consider a finite set of positive integers. Then you can generate Kral Charlier orthogonal polynomials by multiplying this Charlier weight times the polynomial whose roots are the numbers in the set F. Okay, so this is, instead of adding a Dirac delta, this is what you have to do. You have to multiply by polynomial whose roots are positive integers. Well, I conjectured this in 2012 and proved it for some particular case of the set F. Then I proved this for when F is a consecutive, is formed by consecutive integer, and in collaboration with my colleagues Manuel Dominguez de la Iglesia here in the audience, we proved we proved this for arbitrary size. For arbitrary sets. Well, there is a connection between the orthogonal polynomial with respect to this measure and the symmetries I have shown in the beginning. And this connection is a consequence of the following fact. You can find two different determinantal representation for the orthogonal polynomial with respect to this measure. One of these determinantal representation is coming for the general theory of Christoffel transform, which is I'm going to show now. In general, when you have a finite set of real numbers, you can associate to a measure mu the Christoffel function defined by this set, which is just to multiply the measure mu times the polynomial whose roots are the elements of F. Then Christoffel in the middle of the 19th century, and then Sego at the beginning of the 20th century, found this nice formula to construct the orthogonal polynomial with respect to this Christoffel transform in terms of the orthogonal polynomial with respect to the measure mu. Notice that the dependence of x in this determinant is just in the first row, and then in the rest of the rows you just evaluate the polynomials Pn, the orthogonal polynomial with respect to the measure mu, in the elements of the set F, and then multiply and then divide here by this polynomial. It is not difficult to see that they are in fact the orthogonal polynomial with respect to this measure. So since this is a Christoffel transform of the Charlier measure, you can get orthogonal polynomial by with respect to this measure just using the Christoffel-Sego formula, and you get this one where now Cn A are the Charlier polynomials. But as I said before, these polynomial are eigenfunction of a higher order different operator. But it turns out that this formula is useless to prove that, or at least Manuel and me couldn't use this formula to prove that these polynomial are eigenfunction of a higher order different operator. And then we produce another determinantal representation for this polynomial. To produce this other determinantal representation, we use what we have called the method of D operators, which takes into account this remarkable fact that these are going to be eigenfunction of a higher order different operator. And so what we found is the following. Now here entering the picture the involution I defined at the beginning of the talk. You have to consider the involuted set I of F, and then you can construct orthogonal polynomial with respect to this measure using this formula. Again here the dependence of x is only in the first row, and in the rest of the row appear the Charlier polynomial with index in the involuted set and with parameter minus a. Okay, and using this determinantal representation for the orthogonal polynomial with respect to this measure, we could prove that they are eigenfunction of a higher order different operator. Okay, the symmetry of the Casoratian determinant I have shown at the beginning of my talk as is underlying the fact that these two determinantal formulas define orthogonal polynomial with respect to the same measure. In fact, since the orthogonal polynomial with respect to a measure, positive measure are unique except for multiplicative constant, you have this that the both determinantal expressions are equal except for a multiplicative constant. And now you can find this explicitly, this normalization constant, comparing first the leading coefficient of these two polynomials, and then comparing the L2 norm of the same polynomials. The first one is a very easy thing, but the second one is quite difficult, because you have to compute explicitly the L2 norm of this polynomial. But it can be done, and when you do that, you find just as a consequence this symmetry for this Casoratian determinant. Okay. You can use the same method to find symmetries for other families of classical discrete orthogonal polynomial. I'm going to show now the case for the Meixner and Laguerre polynomial, because this case is even richer, because well, I'm going to denote mn for the Meissner polynomial, again normalized so that the leading coefficient is 1 over n factorial. And you can from the Meissner measure, you can generate Kral-Meissner measure using now a couple of finite set of positive integers. Instead of only one finite set of positive integers, you can use two. Now I introduced this Casoratian determinant or Casoratian type determinant. It has two blocks, one block corresponding to the first finite set, and the first block here is just a Casoratian determinant, where the indices of the Meissner polynomial run in the first set here F1. But now this second block is not exactly a Casoratian because it appears here, we divide here by the power of A, and so this is not just a Casoratian, it's almost a Casoratian, but this is not a Casoratian determinant. And now in this second block, the indices run in the second finite set here. Normalized with a constant here. And using the same approach, you can find the following symmetries. First of all, I define the involuted of a couple, just as the couple formed by involuted of each finite set in this couple, and this number as the sum of the number corresponding to these two sets. And then the symmetries is the following. If you chain the couple by the involuted couple, x by minus x, A is the same in both sides, and C2 minus C minus the maximum element of F1 minus the maximum element of F2, then you get that these two rather different determinants are equal the same except for a sign. Now if you take limits when A goes to 1, you can get symmetries for Wronskian time determinant whose entries are Laguerre polynomials. The first block here, when you take limits, gives, as before, a Wronskian whose elements are Laguerre polynomial, the index running in the first set of 1. But the second block gives not exactly a Wronskian, because as I said before, this is not a Casoratian determinant. So when you take limit, what you find is this, which is taking into account the identities for the derivative of Laguerre polynomial. This is almost a Wronskian, but it is not just a Wronskian. And for this determinant, you have this symmetry. If you chain F to the involuted set of F, x by minus x, and alpha to minus alpha minus the maximum element of F1 minus the maximum element of F2 minus 2, then these determinants are the same except for a sign. Okay, so in the second part of my talk, I'm going to show the connection of these symmetries with the state adding and deleting Darboux transformation for certain solvable quantum mechanical system. And to show that, I have to introduce exceptional polynomials. This is a rather a more recent subject. Is coming from mathematical physics, and these exceptional polynomials allow to write the exact solution of the Redinger equation corresponding to certain rational extension of the classical quantum potential. These exceptional polynomials have appeared some 9 years ago, but there has been a remarkable activity around them, mainly by theoretical physicists. And some of them, the ones in blue, have also find these symmetries for Casoratian-Wronskian type determinant for classical and classical discrete orthogonal polynomial. The definition of the exceptional polynomial is the following. You have again a sequence of polynomials which are orthogonal with respect to a positive measure, and that are also eigenfunction of a second order differential or different operator. We have again second order as for the classical and classical discrete polynomials, but the difference now is that there are gaps in the degrees. For exceptional polynomials, you don't have a polynomial of degree n for every non-negative integer. Okay, there are gaps here. You have there are some degrees which are missing. These allow rational coefficient in the second order differential or different operator, and this makes a big difference with the classical case. And in order to get good approximation properties, we also impose that this polynomial, even though there are gaps, are complete in the corresponding L2 space. Well, if you keep in mind the definition of the Kral polynomial, there are a big difference between Kral or in the definition of Kral and exceptional polynomials, because they are coming from very different problems, and in fact, for differential operator, no connection has been found between Kral and exceptional polynomials. What is surprising here is that at the discrete level, the situation is completely different, because Kral discrete and exceptional discrete polynomial are actually the same object. In fact, I have shown that there is an unexpected connection between them, between Kral and exceptional discrete polynomial, which is given by the duality between the variable and the index in the classical discrete family. Okay, so I'm going to show now how to construct exceptional Hermite polynomials. So again, we are going to take a finite set of positive integer, which is going to be the parameter of this exceptional Hermite polynomial. And to construct this exceptional Hermite polynomial, you just take a Wronskian, okay, of Hermite polynomial. The dependence of n is just in the first row, and from the second to the last row, you get the Hermite polynomial with index in this set, which is fixed and which is the parameter of the family. This number here, u of f, it depends only on the set f, is defined like this, and I shift n by this number just because I want this polynomial to have degree n. Okay, so you need to shift this here by u of f so that this polynomial has degree n. Okay, so the problem here is that you don't have a polynomial of degree n for every n, because first of all, n has to be greater than or equal to this number. So the degrees from 0 to u of f minus 1 are missing. But also when n is equal to u of f plus an element of the set f, the polynomial is missing, because in this case you have two equal rows and then the determinant is 0. So there are some numbers n for which you don't have polynomial. Well, it turns out that under mild condition of the set f, this Wronskian, this exceptional Hermite polynomial, are orthogonal with respect to a positive measure, and they are eigenfunction of a second order differential operator. In fact, using this exceptional Hermite polynomial, you can write the exact solution for the Redinger equation corresponding to this perturbation of the potential for the harmonic oscillator in dimension 1. Here what you have is the Wronskian for the Hermite polynomial with indices with the indices running in the set f. And notice that when you make the two derivative here, what you get is a rational function. So you are perturbing the potential for the harmonic oscillator with this rational function. Well, you can now integrate the Redinger equation corresponding to this potential by using this exceptional Hermite polynomial. Well, there are a connection. There is a connection between this exceptional Hermite polynomial and the Kral-Charlier polynomial I have considered in the first part of my talk. In fact, you can construct this Hermite polynomial starting from this Charlier-Kral polynomials. And what you have to do is the following. First of all, you have to dualize. Roughly speaking, dualize here means to change the index n with the variable x. And when you do that, you get you find a new family of polynomials which are exceptional Charlier polynomial in the sense that they are orthogonal and they are a function of a second order different operator with rational coefficient, but you don't have a polynomial for every m, but only when n is in this set. After dualizing, you have to pass to the limit when a goes to infinite, and this polynomial goes to the limit of this polynomial is just the exceptional Hermite polynomial associated to the same set f. Now I'm going to show the connection of this symmetry for the Wronskian of Hermite polynomials with these exceptional Hermite polynomials. And to show that, we have to construct exceptional Hermite polynomial in another form. This form is by applying Darboux transformation to the harmonic oscillator in the following form. You start with the Hamiltonian for the harmonic oscillator, and now we are going to produce a factorization of the Hamiltonian as a product of two first-order differential operators in this form. You take an eigenfunction of the Hamiltonian for the harmonic oscillator. This HF is just the Hermite polynomial with degree f. And now you can produce this factorization where the first order differential operator B and A can be explicitly written in this form. And once you do that, you can generate another Hamiltonian just by reversing the order here. This reversing the order here is what is called Darboux transformation, a Darboux transformation. Now if you reverse the order and make the computation, you get this new Hamiltonian, which is a perturbation. This is the Hamiltonian for the harmonic oscillator, and you are perturbing by this rational function. When you make this two derivative here, this gives a rational function. And now you can explicitly integrate the Schrödinger equation for this Hamiltonian using the exceptional Hermite polynomial corresponding to the finite set given by this singleton. This f here is just the degree of this eigenfunction. Well, you can do that. You can repeat this process for a arbitrary finite set of positive integer, and when you do that, you go from the potential for the harmonic oscillator to this other potential, which again is a perturbation of x squared by this rational function, where this is the Wronskian of the Hermite polynomial with indices in this set here. And again, you can explicitly find the solution of the Schrödinger equation corresponding to this potential, which are given by this exceptional Hermite polynomial I have introduced before. Now, if you can compute the spectrum of energies corresponding to this system, and what you find is that the spectrum of energies are precisely the number for which you have an exceptional Hermite polynomial. And now this is what you have done here, is removing some of the level of energy of the harmonic oscillator. This is the level of energy for the harmonic oscillator, and you have removed here the first level from 0 to u of f minus 1, and also the level corresponding with this number, u of f plus f. This is because this process is called a state-dilating Darboux transformation. Okay, so you have this process to build new potential or new Hamiltonian, which you can explicitly solve using this new exceptional Hermite polynomial. You have this level of energy. And the interesting thing here is that you can do something similar, but for virtual states. Well, this is in summary what we have done using this state deleting process. But you can do the same using this virtual eigenfunction. This is again an eigenfunction. This is the Hermite polynomial, but in the variable minus I x. This is again an eigenfunction, but it's not in the L2, so this is not cannot be a weight function for the system. But this is an eigenfunction, and you can do the same. So you can apply, you can factorize this using this function as before. You can reverse the order, and if you do that for a set, a finite set of positive integer, you pass from the potential for the harmonic oscillator to this other potential, where here appear this Wronskian, and the Hermite polynomial appear in the variable minus ix. This virtual system, you can compute also the spectrum of energies for this virtual system, and what you get is that now the spectrum of energy you have added to the spectrum of energy for the harmonic oscillator. You have added these other energies minus g minus 1, where g is an element of here. This is because this process is called a state adding Darboux transformation. And now what happened here is that if this set G is the involuted set of this F, then the spectrum of energies of both systems are essentially the same, have the same structure in the sense that there are the same holes here and here. Or more precisely, if G is the involuted set associated to F, then the spectrum of energies for this system is the translation of the spectrum of energies for this system by this number. And now, so if you have the same structure for the spectrum, you can conclude that the potential has to be actually the same. And then you get, but if you look at the potential, what you get is that this Wronskian is just the same as this one, where the G's are in the involuted set. And this is precisely the symmetry for the Wronskian of Hermite polynomial I have shown before. Okay, so this is the connection of these symmetries with this state deleting and adding Darboux transformation. Well, I think I have no time to show the connection with the Selbert type formula, so I will finish here. Thank you for your attention.
Any questions?
This is very, very, very interesting.
Thank you.
I have to think about it, but the question that comes to me immediately is, these are quantum Hamiltonians. I mean, it's one way of interpreting them from the physicist's point of view. What about the classical limit? If one take, well, maybe you don't have the answer, but this is interesting, because then the classical model should be some integrable many-body problems.
Yes.
Of a quite new type.
Yes, but I have not considered this question. But maybe it could be new symmetries or new relationship between, because for sure there are more than this one. There is something very rich here, which has been unnoticed for many years, because in the Carli and Sego paper they could discover this. No? But maybe this is a very interesting problem to look at this. Yeah. Yeah. Yes. Of course. Yeah. This is.
And the difference is that you can start, for example, with free particle, and you can put a non-physical level, and you start with one form with one level and so on. And you are putting, then it looks very simple.
It's very...
Because it's the double transformation also with this
Yeah.
differential equation.
Yeah, it's very much related, and in fact there are some of the mathematical physicists I have mentioned.
This W, that is the Wronskian, is called
Yeah,
potential.
yeah, there are some papers relating these things. Yes, right.
Any other questions? Well, if not, let's thank Antonio again.